Okay, let's get started. What's new for this week? For this week, I put up the CSLO essay assignment. That's new. I can find it at the bhacker.com. You can get it right underneath where it says syllabus. You can see the CSLO. I just put this up yesterday, actually. So I believe it was yesterday or Monday. No, I think it was yesterday. So Monday was a holiday. So one thing to note, if you've had classes with me before, the format changed a little bit. It used to be 3 to 4. I changed it to 2 to 3 pages because it's really hard to answer some of these questions in more than 2 pages. And this is double-spaced, so it's really like 1 page to 2 page. So what I'm looking for is preciseness in your answer and not quantity. So give me a good quality answer. And if you're new, what this is all about is it's an essay that you're writing. So you don't have to, it's not like the old CSLOs of the nightmares of ITU days past. It's the future of in terms of the concept. And what we're looking at is you need to pick one. So you want to pick one of the topics below. Don't do them all. There's 9 of them here. You don't want to do them all, just one. And you're going to write 2 to 3 pages double-spaced on one of these topics, and you're going to hopefully give me 3 reference citations to show me something in the literature that you've found on it. It can be out of the course notes, it can be on a website, it can be anywhere you want, because you're going to need to do a little bit of researching, perhaps, to answer some of the questions. Most of the questions are from the course material I've covered. I've put some different ones in there to give you some give you the ability to do some research on your own, to learn above and beyond what I've lectured on already. And you could go ahead and read through the questions on your own. If you have any questions about the questions, you could let me know. But in any case, what we're looking at is defining or looking at how prototyping supports requirements engineering. So anything in regards to prototyping. Also, the next one, structured programming and analysis. How does it help error avoidance? Which is kind of an interesting subtopic, which is, as you know, you may not necessarily be able to write more than 2 pages double-spaced on that. So it's some of them are easier than others. Pick the question you like. You don't have to do them all. You know, what does testing do, and what does it not do? Well, actually, we're going to talk about testing today. So, questions on the CSLO essay or the requirements for the essay? No? Oh, we have a question? No. It was just a stretch. Okay, no questions, and we're going to get started, and we're going to talk about testing today.
What's the due date for this?
Oh, August 16th. I'm going with the 16th for everything. Yeah. Which is a month. More than, well, this is July 16th next week, because Saturday is the 16th, so about a month away. A month away, yeah, that's good. So lecture number 11 is our topic for today. And what we're looking at in lecture 11 is, let me get this guy plugged in too, is the concept of testing. And let's see. Oops, that's what I wanted right there. Lecture number 12 is the midterm exam review. And sometimes towards the end of this week, perhaps next weekend, I'll be putting together the midterm. It'll be a take-home midterm. So because we're right at the midterm time. But I had some people from the weekend section requesting that CSLO, so I put the CSLO out first. But that's nothing is due till August 16th, so you don't have to worry about anything. So lecture 11 is on software testing. And what are we looking at in terms of the objective of testing in a project? We're executing the program to find errors. We're interested in finding errors. In fact, if the testing doesn't reveal any new errors in the program, it's really not effective testing, because there's always errors in the program. There's always bugs. So a good test case has a high probability of finding errors, hopefully. And a successful test finds new errors that were not discovered before. So in terms of what do we test, we can put the software spec, the test specs, everything together in terms of our testing plan or testing strategy. And the results of that particular testing would go into some sort of a check mechanism to kind of say, did we fix it, did we not fix it, where is it coming from, can we validate the error, do we understand where the error is coming from. And then we have testing reports that come out of that that tell us kind of like, what problem areas do we have in the source code. And then we can decide what we're going to fix, essentially. It's not a matter of, it's not different from bug shooting or bug troubleshooting. Can't talk today. It's more along the lines of not necessarily fixing bugs, not necessarily finding bugs, but checking from a higher level, from a black box perspective, looking at what the software is actually doing functionality-wise. And there's many different types of testing, and I mentioned the word black box already, so we'll get into this. And this is going to be way too boring for anyone who's taken a testing class. But let me just highlight a few things on here just to relate it to software engineering, and I'm not going to give you everything you need to know about testing. Save that one for testing or QA. Two main types of testing strategies, however, black box and white box. We could also put glass box in there, or clear box in there. There's just all more terms for white or gray boxes. Black is solid. You can't see through it. You're testing the outside functionality. White, you can see through it. It's clear. That's why they call it clear or glass, because you can see inside of it. That's testing the source code itself, and not necessarily its functionality from a user's perspective or a user interface, but the code itself, the complexity of the code, how the code was written, the loops, iterations, and stuff like that. So for the groups of projects, for your group projects, you're going to be implementing black box testing, and that's where those test cases are coming from in your analysis document, because you're putting together 10, and I'll look at at the end of this lecture, we'll look through an example of what you need to do actually for that, which carries over into the design document. You just add a couple more to it. Or you just, if you didn't do it in the analysis, you're going to do it in the design, essentially. And you're putting together 10 to 15 test cases. I can't remember what the spec is. It probably is 15 or something. And those test cases are black box in nature. So black box testing. So you know the functionality. So you're testing to see if the functionality is working correctly and if any of the functionality is missing. So I'm going back to this concept. The software specifications, that's your requirements document, your requirements and your requirements specifications. That's basically telling you what the system should be doing. And then the test specs are working with the requirements. So you're making sure that you've actually implemented all of your requirements. And you've got every feature that was asked for, that was requested for, is actually implemented. So given what you know what it's supposed to do, you design tests to make sure that it's doing what it should do. From the outside, you're testing the functionality against the requirement spec. And for software, this is the testing of the interface. So it's the input to the system. Perhaps it should also be done outside to change the system. What can be done from the outside, what results for input. And what is the output of the system, what kind of reports are the reports worthy? Are they accurate? Is it actually giving you the right answer? So you're testing the functionality to observe any external behavior that might occur. No knowledge goes into how how it's meeting its goals or anything of that nature, or whether or not the code on the inside is actually working properly. That's left for white box. And white box testing is that you know the code, and given the code, you're testing, is the code implemented correctly? So given the knowledge of the internal workings, you're going through and seeing what's happening inside of the box. And it's a close examination of the procedural level of the detail of what's going on, logical loops through the testing, conditionals, loops, branches. You have the status in terms of its expected values. Impossible to thoroughly exercise all paths. So you're doing the common paths that you can. And actually, as a kind of a side comment, it's impossible to run and test everything in the software, and they call the concept coverage. So the coverage is the entire program. Your test coverage is what is it you're meeting. Are you testing all of the features of the entire program? And if so, how many times are you testing each one, and what percentage of the features you're testing out of each one of the modules or out of each one of the classes or something? How have you broken it out in terms of different sections that you're testing? So you design the test plan to get full coverage, essentially, because you don't want to spend all your time testing the database and not test the website interface or something, or not test the connectivity or something else. Because, one of those little things that could break could totally, it doesn't really matter how often or what you did in terms of testing the database. If the program doesn't work, from the user input perspective, it's not worth doing. So let's see, it can be practical if the limited number of important paths are evaluated, and can be practical to examine the test's important They test important data structures and forget about unimportant data structures. Simple processes, you'd think actually, skipping them would be a good idea, actually. However, you probably want to sample some. So what ends up happening is people create all sorts of different types of tests, and whether or not they're actually all performed is another question. So in terms of Whitebox, this is why there's so much automation going on. If you can get a unit testing or something of that nature done, and you can get this automated a bit more, then you can test more in a shorter amount of time and use less, fewer man hours in terms of getting that done. The Blackbox is easier to do. You can get, it's just users. In fact, your end user, after you've delivered the product, they're doing Blackbox testing for you because they're going to report back and tell you what happens when they're starting using it, and that's what the technical support is about. I mean, they're going to say, well, when I was using the software, it crashes every 5 minutes, and I've got this problem with it, So in terms of who's doing the testing, the end users, anybody could be doing the black box. Who's doing the white box is usually programmers, because you have to understand the source code in order to test the source code. And the programmer's time is very valuable, so you're not going to waste it doing all the testing. In fact, what a lot of companies do is actually hire testing people that are trained programmers to do the white box testing. And those people are going to utilize some tools, because it's one or two guys who are doing it, so they're going to utilize some automated methods to get that stuff done, hopefully. So what and when and what to test. And this is kind of an interesting chart. It's got the project time. That 6 is the slide number. It's not on the scale here. So as project time goes, as we move through the project, we have the level of detail that we know about the project being high and low. So as we go further down, we get a higher level of detail the longer the project goes on, and we learn it because we're learning about the project as it's going through. If we look at here, we've got the waterfall model going on here. We've got requirement specification, we've got analysis, design, and let's say object-oriented design. Usually right after design, and I just kind of threw object-oriented design in here so I could give you unit testing as an example, but any form of design as a category here. By the time the design is over with, really all the testing stuff is over with. All the planning is over with. In fact, it happens throughout the development life cycle. So right in the beginning, we've got the requirement spec, and then over here are red boxes on this side here. We can actually develop our acceptance testing. So it's very classical. It's very common actually to see people do this at the end. So they've gotten the requirements, analysis, design, they've implemented the thing. Oh yeah, let's put together some acceptance testing. And it's like you're going backwards, you're starting from the beginning, and you could have done that right there after you put together the requirements. So if you have like a dedicated testing person, or testing group, that person can start working right there at the beginning with the requirements and say, well, we've got the requirement spec, let's put together the acceptance testing. Acceptance testing is like a checklist. It's usually a black box kind of approach that says, is this feature here? Yes. This feature here? Yes. It's kind of like when you buy something and they go and review it for you, and they go, okay, we got this feature, this feature, this feature, this feature, and this is what you wanted, right? And then you go, okay, and then you pay for it, which is acceptance testing. Right at the analysis stage, well, we could put together the system testing. As we're analyzing it, this is when we're creating those diagrams, the entity relationship, the data flow, the object-oriented diagrams, and we're really understanding, we're analyzing it from a component level, from an architectural level. Well, we have all that stuff we're looking at that stuff right now. So we could take that and turn it into system testing. System testing is testing the module interfaces between all of the different components, how you've got it broken out. And when I say start and do the system testing, you can create the acceptance test. You can't get the customer to accept it until you actually deliver the product, which means you're writing up the test plan and you're performing the analysis to do the acceptance testing, creating the checklist or creating the items that you're going to be evaluating. And then in the analysis stage, you're creating the system testing. So you know which modules you're going to need to test, which ones are going to interface. And then in the design, you can do the integration testing. Because you know this class is going to work with that class, and that class is going to work with this class over here, and you've got it all laid out in terms of the design. So you can integrate the components and put together the test plan, essentially, for the integration. And then while you're doing the object-oriented design, which is kind of leading into the implementation at this point, that's when you can do unit testing. And a classic example of that would be if you're writing the program in Java to implement something like JUnit and put that in there to do some automated unit testing, which is an open source tool that's very popular because, well, it actually takes almost twice as long if you start doing unit testing when you start to actually create the classes and implement it, because you have to do two instead of one. You write the real class and then you write the JUnit test that goes along with the class. So that's a lot of work. So that's why people don't like to do it. And that's why we have automated tools out there that'll do it for you. That'll take the written class, create a kind of a template out of it, and then you can fill in the blanks with what you need to do in order to complete the unit test for it. But as you can see, we have activities that are occurring all the way throughout the software development lifecycle. It doesn't all happen at the end, which it should not all happen at the end. If it does, it won't get done. It's like trying to do the entire project in a week. It doesn't kind of work that way. And in terms of the high and low level of detail, as we get more detail, we get more specific types of tests that come out of it. And we kind of move from a black box to a white box in a lot of different ways. So here's the different types of tests as I've just kind of reviewed for you a few minutes ago. I've been talking about unit testing. And generally that is white box, and it's usually done by the programmers. It's really hard to get sophisticated end users who know programming. If you do, they're probably going to write it themselves. Why would they be hiring you to do this? So it's usually going to be the programmers that do it, and everyone can tell you the programmer is like the worst person to actually test their own code, because you're never going to see anything. Nothing is ever going to be wrong with it, and you're not going to follow it, you're not going to see it. You have your blinders on. So it's not usually the people who are implementing it, it's a different set of programmers. Integration testing can be both white, and it can also be black box. So it's done by the programmers as well, as they integrate the code into the code base. And what I mean by black box here is you can actually kind of test it black box first. If you find an error, go to a white box approach. So as you're integrating the units, if it's working, leave it alone. If it's not working, then go inside and look into the code from a white box perspective and see what can be fixed. Maybe there's a method call that's wrong, sending the wrong type of data or something. Or maybe there's missing functionality, which is usually the case in the integration. It's usually something is not integrated correctly, there's something missing, some connection. And then we have functional and system testing. It's mostly black box. It's recommended that this be done by external test groups. This is where if you work in QA testing, you can do system testing. And it's great to bring in people from the outside who don't have blinders on, who aren't personally involved with the source code or with the application itself, who can really do a nice functional evaluation of it and tell you if something's actually working properly or at an acceptable level. Programs do make errors, so if it just crashes every so often, it might not necessarily be a big deal, but it might be a big deal to an end user. So the external group, they don't have blinders on. So it's mostly black box, so that the testing is not corrupted by too much knowledge as well. Outside people don't know what it's supposed to do. So this is interesting when you get functional system testing and you give it to focus groups or you give it to outside. And then they start using the software in a way you've never imagined. And then they start discovering new features, and then they go, wow, look at that. If you go to this screen first, you can bypass the password. And they find the loopholes in the system, and they're not normally actually looking for them. It's just their intuition is telling them to go to this option first and then go to that option, which is kind of different because they're seeing it from a different perspective. And usually they find, oh, if you go to this screen first and then you click on this option here, and you do the back button, you get logged in without even having to log in. Ooh, or something, weird that happens, which could cause a major problem in terms of the functionality. Acceptance testing generally done by the customer. Obviously, customer is a representative. Let's see, of their environment through the GUI, definitely black box. You're not going to do white box to a customer, which is kind of interesting. A lot of people like to show customer source code and stuff. What are they going to do about? What are they going to do with it? They don't care. Sometimes even if they're not competent enough to actually do the acceptance testing, they'll have one of their head engineers or something do it for them. Appoint a person to actually accept it, which, puts the responsibility on that trained professional who's supposed to know what they're looking at, rather than the business person or the IS person who requested the system to be built. So our testing process begins with a few different iterations, and this is an iterative approach. And as I mentioned before, we have the test preparation, and then we have the test execution. So here we have the design of the test cases, which is usually done in the analysis, which is where you're doing it. The output of that is a set of test cases. And then the design of the test cases generally leads into some sort of a preparation of the test data. We've got to have, input, some fake account numbers. So if you're testing a shopping cart application, you're going to have a bunch of fake, maybe Visa, MasterCard numbers or something, and you're going to have some transactions that you're going to have to go through, that you're going to have to test through, maybe some samples. After you have the test data ready, and after you've prepared it, you've got this box that says test data, you've completed it, and then you're going to go in and you're going to run the program with the test data, and you're going to come out with some test results. Hopefully, and those test results are going to be compared with other test cases and with the test case itself. And then you're going to have some test reports, and you're going to save those reports. The common thing is people throw away the reports. Oh yeah, it's all working fine. And then they get rid of it, they throw it away. It doesn't become part of the documentation of the software project because it was, unrelated for some reason, or that was felt to be unrelated. But what ends up happening is when you go back through and make a change, it can actually help you. Because at the beginning, this is the first version that came out, so you've made a change, you're going back through and you're doing what's called regression testing. Because after you've changed something about the software, you have to complete the entire testing process all over again. I mean, everything outside of acceptance testing. And as you're doing that, you can kind of compare what happens now with what happened before, but if you don't have what happened before, it's kind of impossible to do that comparison. And something that might be failing now could have failed before. You could have had a reasonable explanation for it, and it wasn't something that changed. So in terms of planning the black box test case, we're going to put together a grid, and you're going to do this for your analysis document. So what we're doing here in terms of the testing that you're doing for your project deliverables, we're only doing test cases, which is kind of a cross between system testing and integration testing, mostly system testing. You're not going to put together any acceptance, you're not doing any unit testing. We're going to do like system testing, which is black box in nature, and it usually consists of a bunch of test cases. So in your analysis document, you're going to put together 15 test cases, and you're going to put together what's called a test grid. And we're going to go through an example of how you put that together. So when you put it together, it's related to your project. And normally there's about thousands or so of these suckers, and usually they're categorized out. Sometimes they're labeled by the order of your requirement specification. So if you have section 2, database 2.1, this table, 2.2, that table. So you can go in your test case numbering, you can go 2.11, 2.12, 2.13, and there's only 1, 2, 3 cases that are all related to that particular feature. Because what we want to try and do is get full coverage. So you're not going to get full coverage with 15 test cases, by the way. You're going to get, I don't know, one feature maybe. If you're lucky, you'll get a whole feature covered in 15 test cases. And we'll see why in a few minutes. If you break it down to how it's supposed to be, it's hard to get 15 test cases to actually test anything because it's just too broad. So look at the requirements, the problem statement. And so you don't even need your finished program in your analysis. You're working with your requirements document. You're not working with anything, which is why you can do it in analysis. Said another way, test cases should be traceable to the requirements. So the test grid itself contains an ID for the test, describes the inputs, the expected or the predicted results. Obviously, you're not going to have any because you're doing the analysis right now, and you're not even going to build it. You're doing a prototype, so you're not going to have any predicted or expected results. And you're not going to have any, well, you might have predicted expected results, excuse me. You're just not going to have any actual results because we're not actually building the software. Which is interesting, some students have given me actual results before. And well, where does this come from, this actual results? That's because they did their project on an application that already existed. And so they mimicked the whole thing, and then they tested the application or something. I don't know. And it doesn't give you any bonus points to put in actual results. It actually works in the opposite direction. So your analysis reports should use the following format. You've got the ID, the input, expected results, and the actual results, and this is going to be blank. So if you want, you could leave it out, or you could put it in and leave it blank as a template that you're going to use. Blackbox test planning. Okay, so the inputs must be very specific, and the expected result must be very specific. One input leads to one output. And you have to write the test case so anyone on the team can run the expected test and get the exact same results for the sequence of events. As an example, passing grade. Input field, the correct input might be a grade is equal to 90 or a grade is equal to 20. Okay. Incorrect input might be passing grade or failing grade. Because what's a failing grade? What's a passing grade? So it leads to interpretation. So that would be a bad example of input. So the test case grid, the last section of your analysis document, is going to have 15 of these suckers in there. And as an example here, passing grade. So we have grade is smaller, and this is ID number 1 and ID number 2. We're not linking this to a requirement spec, and you don't have to do that for yours either. So you do not have to link it to your requirements document. You can just create a standalone numbering system. And you can use number 1, number 2, number 3, all the way up to 15 if you want. In terms of the input, the grade is smaller than 70 or the grade is larger than 70. Expected results, fail the class with less than a C, pass the class with at least a C, and leave blank until tested. Seems pretty simple. And here's the bad test case example. What is a failing and a passing grade? And the problem, the input, the value is too vague. We don't know. Because we can have more. Because think about this. You're going to design this test, grid. You're going to print it out. You're going to give it to a TA, or you're going to give it to, a assistant or somebody who's not involved really in the project, who's going to run this for you, that doesn't know anything. So they're reading what's on the sheet. Input, a failing grade. Well, what's a failing grade? They're going to make something up. So you don't want them to think. You want them to actually type something in that that's going to lead to an accurate result. And you also want to think about, in this particular example, we didn't talk about or didn't consider bad test cases or failure test cases. We can test to see if something fails correctly. What if you don't enter in a grade? What if you leave out this piece of information? What if the input's in the wrong type? So you expected an integer, but you put in a float. You're expecting a character. You got an integer instead or something. What if the customer takes an illegal route through their functionality? So you open up Word, and instead of doing file open or file new, create a document, you decided to print first. Well, actually Word figures that out, just grays out the option. Won't let you print anything. There's nothing to print unless you have a file open. What's mandatory fields? What if they're not entered? What if the program is aborted abruptly, or the input or the output devices are unplugged? It's interesting. You're reading a file from a USB disk, which is kind of interesting, actually. You pull the USB disk out. Shouldn't the file go away? Doesn't. Which I think is kind of wrong, actually. If you're in a music player and it's actually using the USB disk, then the file you'll get an error message from the music player. But if you open a file from a USB drive in Word and you pull the document, you pull the USB drive out, the document stays open. I think that would be a bug, actually, because how are you going to save it? We can do a save as. But, well, the idea is to eliminate any problems or any errors, because Microsoft wants people to feel good about their programs and software, which is kind of interesting, because you don't want error messages. You want people to think it's reassuring. You want people to think that they're doing something correct when they're using their software. So you can use a flowchart to actually figure this stuff out. So mapping the functionality to a flowchart makes the test case generation process a lot easier, because we can just take each one of these routes. If x is larger than or equal to 0, or if x is smaller than or equal to 100, or check if it's true. if it's false, and then each one of these ends up turning into a test case. And during the analysis, you might actually have a flow chart, or you might have an entity relationship diagram, or you might have a data flow diagram or something that you might be able to use. Feel free to use all your documentation. It'll make your test case generation a lot easier. A lot of people don't like to do that. They put all the documentation over here, and then they just write test cases, like from the head. You know, if you do that, you're gonna like leave out all of the most of the functionality, and you're really only thinking about certain functionality that you want to test, and then you forget, oh, what should we test, like the OK buttons and stuff, and then you leave something, and then the customer runs the program, and they go, well, the OK button doesn't work. Didn't you test this thing? You're like, well, I didn't think about that. I didn't test that feature. So there should be a one input that leads to one output. ABC leads to XYZ, the code, with some inputs and outputs that are the same. So a piece of code that inputs ABC is going to produce only one output. So one-to-one testing, each input has only one valid expected result. So to check a valid ATM card, the following is not correct. And let's kind of see why. And what ends up happening, and I get students who do this all the time, they give me test cases, and they're just like this, actually. So ID number one, input, read the ATM card. Okay. Expected result. If the card is valid, accept the card and ask for a PIN. Well, that makes sense. If the card is invalid, there's no ATM card, exception is thrown, and the card is returned to the user. Well, that makes sense. So logically, people read that, what's wrong with my test case? There's nothing wrong with it. Well, you can kind of see where you've got two expected results, and you're not combinating each one of them. And you can't test. They're all in the same category. You can't actually test a valid card or an invalid card in here. So that's really two test cases. So that is reading the ATM card that's valid and then reading an ATM card that's invalid. And then if it's a valid ATM card and accept the card and ask for a PIN, if it's not a valid ATM card, then no ATM card exception is thrown and the card is returned to the user. Like you put in a gas card, not an ATM card or something. So test for the ATM card, we have two separate. So what ends up happening is a lot of students will take this route because, well, you read the ATM card, but reading an ATM card as a piece of input, well, we'll put a password in. You know, you could probably break out a password correctly. Or incorrectly. You know, you could probably make about 10 test cases out of a password field. Is the password long enough? Does the password, you know, let's say you're going to ask the user to enter in a password that they're going to save as their password. Well, did they enter in the same password as the username? You know, most programs aren't going to accept that. Did they make a password of the right character length? So that's two test cases. It was the right length. And maybe a third one might be, did it contain anything outside of characters? Does it have numbers or special symbols? And there might be 3. Does it have any invalid characters in there? That might be number 4. Is the password, has it been used before? That would be number 5. Number 6 is the user password not been used by this user but by other users? That would be number 6. And if I don't know if I can come up with 4 more on that. I probably could. Let's see, is the password a person, place, or thing, or a concept? You know, an unacceptable password. That would be 7. Oh, I got 3 more to do. Is the password easily guessable? Is it using so many characters of the same type, like 111111111 in a sequence that's easily guessable? So that'd be number 8. I don't know. I got 2 more to go here. I don't know. Well, I could almost come up with 10. I got 8 easily. So if I thought about it a little longer, maybe I can come up with 10. But that's all on checking the input for a password. So you can kind of see that you can probably come up with 15 test cases on one feature. So I'm not asking for that much. Here's another test case. Let's talk about getting the PIN, going back to our ATM example. The input is a 4-digit entry, let's say, of a stolen card. Expected result, stolen card exception is thrown. So you're reading the ATM card, and you're reading the invalid ATM card, and let's say you have an invalid PIN that's entered in. Stolen card exception is thrown, and the card is destroyed. Well, What if it's the right pin but for the wrong card? That would be a different test case if you're checking for that. What if it's the right pin but you're a digit short? You're one short. So actually, that happened to me at a gas station one time. You know, it asked me to re-enter my pin. And I'm thinking, well, why would it ask me to re-enter the pin instead of telling me that the pin is invalid? Because I was missing a digit on the end. So it knew I had the right pin, but the entry wasn't correct. It didn't catch the last digit. It was close enough. But so it depends on how much matching they're doing. And then I re-entered it, and it let me pump the gas just fine. So it's kind of weird. Some ATMs actually, you know, verify your PIN again, like, or, you know, or let's say you're moving from one menu to another. They used to do this a lot. I don't think it actually happens anymore. You're using an ATM machine. If you go from a withdrawal to a deposit or something, they used to ask you for your PIN again in the old days to verify that you were still the user. Because people would, like, leave the ATM machine for some strange reason. Oh, here's my money. And they'd go and they wouldn't get the card back, or they wouldn't, you know, they'd leave everything in there. And somebody else would come up and say, ah, look at that. And they'd ask for the PIN again to verify that you're still the same user using that machine. So nowadays, actually, they're playing for idiots because, or they're designed to be used by idiots because after you're done with the training, so, you know, they should just spit everything out anyway. But some actually don't. They sit there and wait for you to do something. And then they time out and they spit everything out if you don't do anything quick enough. Because what they don't want you to do is leave and your card's in there. And because that would, you know, obviously be a security problem. But people do leave. People still today leave ATMs with cards inside of them. You know, they're talking on the phone, they're text messaging, they got 5 different things going on at once. They slip their card in there and they get their money and then they leave. So, shouldn't the ATM be responsible for spitting the card back, you know, spitting out the receipt? So now actually the money's the last thing that gets sent out, I think, or hopefully. But no, actually not Wells Fargo. You can get the money and you can walk away without getting the receipt or the card. Which is interesting because I went to a Citibank and that was the money was the last thing. I'm like, wait a minute, I haven't got my money yet. Here's your card, here's your receipt. Ah, here's your money. Give you the money last. But that is actually a result of somebody doing some interface testing, looking at this going, how do we prevent that problem? And it's not necessarily a problem with the program, it's a problem with the way the program is being used. But if you think about it, it is a problem with the program. If you can use the program in an unsafe way, and you have some security issues, then it's, although there's nothing wrong bug-wise, error-wise in the program, the logic's not correct. So here's after the testing is being performed, the results are recorded. Here we have the reading the ATM card. We accept the card and ask for a PIN. And then we have the actual results here. And sometimes I see some variations. We see a pass-fail box right here instead of the actual results. Or we see one next to it that says pass-fail. Because we can have a failing test that has some actual results that are different than the expected results. But they're not a problem. It's just like you accepted the card and asked for a PIN number. So this accepted the card and then didn't ask for the PIN number or something. At least you know, well, it accepted the card. Or it doesn't validate the PIN or something. And so if you have the actual results, then you have the history of what happened. Although you didn't see it happen. You have a log, hopefully. And then you can have a column on the right that says pass-fail on it. And then, you know, you can know whether or not something passed or something failed. And you're looking for a certain percentage of pass, and with the, you know, the exception of, you know, you're going to have some failures. And then if you organize the test cases, and here we have the status here. If we organize the test cases in some sort of logical pattern with the ID numbers, we can look for failing, which feature is failing. And if we had this organized by feature, we would know that the ATM card is being, and the PIN is being tested here. And here we have 2 failures. We know there's probably a problem with this module, with this particular functionality, and we know where to fix it. So here we accepted the card and asked for the PIN on a no ATM card. So that was a failure. Stolen card, we accepted the card and asked for a PIN. But how do you know the card's stolen? That's an interesting one. So it doesn't really know. Unless it's going to do eye retina scanning or something. I don't know how sophisticated these ATM machines are these days. Okay, so this leads into the concept of validation and verification. I know I've talked about this in software engineering too, so this is going to be a repeat for those of you who took that course, but the overall concept, and probably most of this testing stuff, is a repeat as well, which is what happens when you take two before you take one. But in terms of what the concepts are, this is what our testing is supposed to be accomplishing. And we can't say that Whitebox or Blackbox does either validation or verification. But what we can say is we can get verification and validation out of a combination of both, and after putting together an actual test plan. So the test plan would have multiple different types of tests in them, of different categories, testing different features about the software. So testing is performed during the system implementation stage, and the results are delivered in a final report that's used for acceptance. So the implementation tells us that we've implemented all of the required features, and whether or not those features are working or not is going to be hopefully in the final report. And then the test report provides the verification and the validation for the software program, and the definitions are, in terms of the verification, are we building the product right? The software should conform to a specification. Or validation, are we building the right product? And the software should do what the user really requires it for it to do, and it's a valid solution to the problem. And that's essentially what we're trying to get at in terms of the concept. So, and believe it or not, that's all we have to be concerned with in terms of our project in the analysis document and what we're trying to accomplish with the testing. So lecture number 12 is on the midterm and midterm exam review, but we're having a take-home midterm for this course, so I'm going to skip that lecture. But when you take the midterm for this class, you can probably look at lecture number 12 on your own and see that I'm going to go over in that lecture, well, in the lecture I would have gone over like what was covered on the midterm, but you're not taking it in class, so. And I haven't actually written the midterm yet. I'm going to do it before the end of the week, and it'll be available to you. So moving right along to lecture number 13, we're looking at the software design and the design specification document. This is the last lecture of the design, actually, because what we've done in terms of the analysis is we've covered the design. But this lecture puts the pieces together in terms of the different components, and I believe a couple weeks ago we went through, or maybe it was even as close as last week, we went through the design document, I believe. Yes, we did. And we looked at architectural components, component N, component 1, 2, 3, breaking out. So we come up with, when we put together this design document, we're using the analysis document as our template or as our rough draft, if you want to use it, and we're reformatting it. We're keeping the beginning sections the same, and then we're starting out with an architectural design. I'm going to talk about that in a few minutes. And then we're breaking that out into subcomponents. And we're going from component number 1, here's a description. Here's what's going on with this component. Here's the data structures it contains. Here's the data format. Here's the processing that's going on. Component number 2, here's the data, here's the processing. Component number 3, data processing. And we're also working with the user interface design. And we're also working with any remaining object orientation and any type of implementation details that we want to provide. So the design is really the blueprint for the implementation. So you give the design document to the people who are going to be doing the programming. You say, here, build this thing for me. And then they build it. And it comes back and you get what you asked for without having to explain anything to them. Sometimes there's some questions about the design document, and the developers can come back and say, hey, what is it? What do you mean by this? And those little clarifications kind of help the design team build a better design document next time, because then they know, oh, we know we need to include this, and this in here instead. We need to reformat something because people don't understand this. So it's an iterative process, and every time you make a design document, subsequent design documents actually come out a little bit better. So by definition, design is the problem-solving process. And you're describing a way to implement the system's functional requirements, because the non-functional should be fairly self-explanatory, and it's based on the functional requirements that you've come up with, and also respecting the constraints of the non-functional while adhering to general good quality principles, hopefully, and building quality into the design. So I'll talk about a few quality factors today, like cohesion and coupling and things within the modules, which kind of want to reduce the number of interdependencies that exist between the modules. You want to make sure that the modules themselves or the system components are sort of like self-contained and they only have one identity and not serving multiple purposes. Which are some of the good design issues. So design is actually a series of decisions that we come up with. Your analysis document has a lot of stuff in it. It's all diagramming. So you take that and you make some decisions out of it. You come up with one best way of doing it. You can also put a section in there that says, alternative approaches, as I mentioned like last week when we went over the document. And in there you can say, well, we thought about doing it this way instead. And we know it can be done this way, but we went this approach. And then that just documents the idea, like if we run into problems, we might want to do plan B, and that's the alternative solution. And we're not going to go and make two solutions out of this. We're only going to suggest it as a path to be taken for the continuation. So designers faced with a series of design issues, sub-problems from the overall design problems. You've broken the problem out, hopefully, into different modules. Issues with many different alternative solutions that might exist, different options, trying to pick the best option, which is really a decision process, making a design decision. And the process involves choosing the best option among all of the different alternatives that might exist. So in terms of making the decisions, to make each design decision, you actually have to have knowledge of the requirements, the design as created so far, the technology that's available, the software design principles and best practices that exist at the current time, and what's worked well in the past, which is why it's nice to get a team that's done a project before, because then they have the history and they know what, they've been making network applications for a couple years, then they know what works, and then they know they make better decisions. So the design document, as I mentioned before, is broken out into components. Component 1, Component 2. And this is how you're designing the design document. And that's kind of a play on words. This is how you're creating the design document. You're breaking it out into components. A component is a piece of software or hardware that has a clear role. If you're looking at a client-server program, components might be a client component and a server component. If you're looking at a telecommunications program, you might have terminal component, modem component, media component, different pieces of the system. So the component is isolated, allowing you to replace it with different components of the equivalent functionality. So one server could be replaced with another server, or one peer with another peer. Many components are designed to be reusable, and conversely, other platforms, special purpose functions, and things that might be replaced with in terms of reusability. And then we have the concept of the module. So the component that is defined in terms of the programming language interface. Modules are classes, objects. Components are system pieces. And this is the definitions for these things. And people confuse it all the time. You can have different components. This is why in the design document I didn't say module 1, module 2, module 3. But a module can be a component. So in the component diagram, you can say object-oriented design component class, which would be an implementation from a programming language perspective of a component. So the module, example methods, classes, packages, those are all modules in Java. And in fact, they're called modules. They're not really called components. And sometimes when I use the word component, people go, what are you talking about in terms of a component? Modules? Module is a component, but a component doesn't have to be a module. Component can be something else. Component can be a hardware device. It doesn't have to be software. But modules are normally software-oriented, and it's normally implementation in terms of the programming language. And then we have the system, and the system boundaries to think about. So the system is the logical entity having a set of defined responsibilities, objectives, and consists of hardware, software, and anything else that might be included in terms of the system. Scanners, cell phones, hardware devices. So it has specifications that are implemented by a collection of components. So a system is not necessarily computerized, but most of them are these days. It's a piece of the software. Sometimes you're building the system. You're building an accounting program. And that would be, the system would be the full program. And which consists of all of the components that you're looking at. And the system continues to exist even if the components are changed or replaced. So you have an accounting program and you're not going to use that reporting module anymore. You're going to replace it with Crystal Reports or something, and you're going to create something brand new out of it. And then what you're looking at is a replaceable component of that particular system, and in that particular case, you're looking at more along the lines of the system definition and not necessarily looking at it from a component level. And the goals of the requirements analysis is to determine the responsibility of the system, which is what you've done in your analysis. So your analysis was focused on the system, actually. We know the system already. Once we know the system, we can break it out into the components, and then we can do the design of each one of those components, which is what we're doing in this design document. It's a big difference between, and the reason why I called it the analysis document, which doesn't exist in the real world, and the design document, is you have to actually do the analysis of the requirements to come out with your definition of the system, your definition of the components. And then that's what you're documenting in the design document. Nobody really cares about how you define the system. All that stuff is done in the background. And then the result of all that thinking is that design document that you've put together. So systems have subsystems as well, which are smaller parts of the system. So part of the larger system is definite interfaces for smaller systems. Now we have a top-down and a bottom-up design approach. We're taking sort of a top-down, because we're starting with a conceptual architectural design, a system diagram, and we're moving into component 1, component 2, component 3. And depending upon how you design the design document, or there's a design again, how you create the design document, then it's going to be read a certain way, and then that might actually drive the implementation a certain direction. As an example, you can start with a big picture. And from a programming perspective, you could build the big picture from a top level and then work down into each one of the features of the system. Or you could skip it and go, and that would be top down, or you can go bottom up and say, I want to build the little pieces. And we're going to put the little pieces together and we're going to make this big picture out of it. In fact, a lot of programmers, believe it or not, program bottom up. Because if you think about it, you're writing an application for a school assignment, and the application has to do file encryption. First thing any student's going to think about is, what kind of algorithm am I going to use for that file encryption? And they start working on that algorithm. And you define the algorithm, and you get that created. Okay, now how am I going to make the algorithm work? And then you have to build the other components. Well, let's see. You have to take the file in. Okay, I got the file in. And what you're doing is just working with a small level of detail of that algorithm, and you're working it up. Now you have this big program with options and features, and and one of them, lo and behold, is to use that algorithm at the bottom, which would be a bottom-up design, which is how programmers think. But unfortunately, software designers think top-down. They're looking at the big picture, and they're breaking out the big picture into smaller components: component 1, component 2, component 3. And then they're going, okay, for component number 1, here's all the details. For component number 2, here's all the detail. And you can actually take a top-down design and implement it bottom-up. Only problem is, if you're going to start your testing before the software is finished, you have a different strategy. Because if you're doing a bottom-up from working with the smaller levels of implementation, how are you going to test it? So you're probably going to start with your Whitebox first. And then you're going to have all that stuff designed to work with modules, and you have to put dummy components in the test. If you're doing top-down, you're going to do Blackbox first, and you're going to test the functionality, because all the insides are missing. You just have the big cover, the higher level view to actually work with. So your testing strategy is going to be different. So you don't really specify in the design document how you want it implemented. How the programmer actually attacks the problem is going to be different. You can certainly guide them in the right direction, but you can't really predict what's going to happen. So some of this stuff doesn't happen until the implementation actually gets started and you start seeing what the implementers have started doing. And then you switch your strategy to accommodate what they're doing, so you don't wait until they're completely done before you test something. So let me go through the slides here on what it is I just mentioned, and give you a little bit more details about each one of these approaches. Top down, the first design is usually the very high level structure of the system, which is what you've done in your analysis. And then you gradually work down into the smaller level decisions about the low level constructs that might exist, and you finally arrive at the details, such as the format for a particular data item, the individual algorithms that are going to be used, things of that nature. The bottom-up design, you make the decisions about the low-level utilities, the algorithm, the design of the modules, the lower-level details, and then you decide how you're going to put them together in the higher-level constructs to create the big system out of it. Most people actually do a mixture of top-down, bottom-up approaches, and they're not going to go one or the other, because you don't know what's going to happen. You don't know how the implementers are going to do it. So the design is actually, your design document is structured top-down, but you could actually do a mixture. You could put in a lot of lower-level details and then work it upward as well and show both views of it. Top-down design is almost always needed to give the system a good structure, if you think about it. Because otherwise it's kind of like, you're organizing your garage, as an example, and you got garbage you're going to keep forever, because you can't part with it. And, you got all these banker boxes, anyway, so you decide, oh, you know what, I'm going to organize the garage, I'm going to put all this stuff in boxes, right? Well, wouldn't it be nice at the beginning to figure out where you're going to put the boxes? Because, a lot of people actually, they have center of the garage, they put all the boxes in there, and then they fill up the center of the garage, and then they decide later, that would be bottom up. You're starting with the individual box that you created, and you haven't decided where you're going to put it yet. And then there's the other set of people that would clear the space for the boxes. This is what I would do, actually. Decide where I'm going to put these boxes. Clear out the area in the garage where the boxes are supposed to go. Start there. And then this is the big picture. I'm going top down. I'm taking each one now and organizing, and putting everything in boxes and putting them up where they're supposed to be, so there's no pile in the middle. I'm slowly working it this way to eliminate all of the clutter and organize it, which is a different approach. You're just starting in a different spot. Instead of starting at the end unit, you're starting at the top unit, which makes a lot of sense. So, in terms of the mixture, when you decide how you're going to actually do the approaches, the top-down design is needed in order to get a good structure, which means I've got structure started in that garage. I've got the starting place. I know where the boxes are going to be. And the rest of the structure just falls into place until eventually the garage is empty or cleaned up. The bottom down is normally useful so that you have reusability components that can be created. So if I start bottom down, going back to the garage example, and I decide I want to put all the textbooks that I no longer read in a box. Actually, better yet, I'm just going to donate them to Goodwill. So I take all the textbooks out of the place, and I stick them outside of the garage. Then I decide, oh, I want all of the, bicycles, parts, and pieces. I want them to go into this box here. And then I got boxes up all over the place, scattered all over the garages, and half of them are empty because they got, this one's got bicycle components in it, this has got old kitchen utilities in it, this has got clothes in it, this has got, it's all organized. But it's all over the place, scattered out. But then at the end result, I have boxes of like kind that I can put labels on, and everything's organized. Versus, I just need to fill the boxes to get this clutter away. You can't see what's going on. You don't know what's in each one of the units. Each one of the modules isn't really self-identifiable at that point. If you're just looking at the big picture and you're not looking at the finer details of what's going on, you could just be starting here and clearing it this way. Whatever you happen to run into first is going to end up in a box. So, in software, believe it or not, it works the same way. If you take both approaches, start out, which is what you're doing in the design document, and build a top-down, so you've got the overall big picture, you've got all the components categorized out, and then you let the programmers do a bottom-up from there. Then they can decide this belongs here, this belongs here, that belongs here, and they build self-contained components that are reusable, that have a better structure to them. If they build it top-down, they might not necessarily build the same structure out of it. Because you might have a feature that could belong in two different areas, but you put it in this module instead of that module. And then you decide, you have to make some of those decisions, and then you can change it in the future. So different aspects of the design. We have the architectural design, as I mentioned before, is the big picture. It's the division into the subsystems and the components. We have how everything's going to work, how these will be connected, how they will be interacting, their interfaces and stuff like that. We have the class design, various different features of the classes if we're doing an object-oriented design. If we're not using classes, it could be modules, procedures, functions. The word class in there is just to say module. Probably should change the wording. User interface design, which is your last section of that document. Maybe some algorithm design as well, designed for computational mechanisms that might exist. Maybe some protocol designs if this is a, let's say it's a networking application and you're using TCP/IP or something. So principles leading to a good design, these are the best practices. Overall goals of a good design. What makes a good design? Well, it's actually the same thing that you'd normally think in terms of evaluating a program. It's a good program. Ensuring that you can actually conform to the requirements and you've actually implemented all of the requirements. That would actually be a good feature. Accelerating development, increasing the qualities. So some of the qualities that we might have would be usability, efficiency, reliability, maintainability. And those qualities should hopefully look familiar to you by now. I've reiterated them in almost every class I teach because that's how you judge software, essentially. That's how the world judges software, by those characteristics. So what you're doing in terms of the design from an overall goal is you're dividing and conquering, which sometimes is referred to as functional decomposition, is another term used for it, but dividing and conquering is more layman term. So you're trying to deal with the big picture, but you break it out, so you're dealing with a smaller series of little pieces that add up to the big picture. So you can separate people out so they can work on each individual part. Because what you don't want is to hire a bunch of people and have them stand around and go, are you ready for us to do something yet? So a good project leader actually divides it all out. It says, this group is working on the database, start now. This group is working on the network stuff, start now. This group, and they're all working simultaneously instead of one guy trying to control the whole project, assigning, delegating out work by work without dividing out and working in separate groups, hopefully. And individual software engineers can be specialized as well. You can find database specialists, architects, database architects. You can find programmers. You can find networking people, which makes job satisfaction better because the networking people aren't doing programming. They're doing networking stuff, which they like, hopefully. Otherwise, they shouldn't be doing that job. And then each individual component is smaller and therefore easier to understand, easier to know we've got it correct. Parts can be replaced, changed, without having to replace the entire system. So you can change parts in and out. In fact, you don't have to wait for all of the parts to be completed. You can put dummy modules in there. So you can start your testing and start your work. You're not waiting on anybody, essentially, if everything is broken out correctly. So ways to divide out a software system. We have a distributed system that's divided out into clients and servers. Maybe something that's divided out into subsystems, maybe a subsystem that's divided out into packages, perhaps. Maybe the packages are divided out into classes, classes divided out into methods. It just depends on the level of abstraction as to what you're talking about, what you're dealing with, in terms of how you're going to break it out. And here's the basic concept of cohesion and, and consistent. Well, actually, let's just start out with cohesion. When you want to increase the cohesion where possible, so this is something we want to increase, and what we're talking about is making a subsystem or module as high cohesion. It has high cohesion if it keeps together things that are related to each other and keeps other things out. So a print module should only do printing. It shouldn't do scanning and faxing. So accounts receivable should only do receivables. The module itself. We want a high level of cohesion. It keeps it so it's reusable. It promotes reusability. If we had a class, a module that did printing, we took the printing module out and we replaced it with another one, and lo and behold, we have an error that's introduced because that one also did scanning. But not all printing modules do scanning. It's kind of similar, but someone decided it was the same. So if we have a scanner and a printer, we can interchange both of them. That's a high level of cohesion. It's a good design principle. So you're kind of making more modules out of it if you think about it, because you're taking one big one and you've broken it out into smaller self-contained, self-identifiable modules. So the number of modules doesn't really add to any factor in terms of goodness or accuracy or efficiency. But the self-identification, the keeping things that are similar together is a little bit higher level. Makes the system as a whole easier to understand and to change. So, well, it's kind of like finding stuff in the garage. If the box is marked bike parts, you're not going to find tennis shoes in that box. You're going to find bike parts, hopefully. And if you pull the bike parts out and you decided to give that away to Goodwill, you've given away all of your bike parts or your textbooks. You haven't given away any clothing or bike parts or shoes or anything else that was associated with that, not associated with that concept. And then we want to reduce the coupling. So we increase the level of cohesion and we reduce the coupling. And the reduced coupling means we have reduced the number of interdependencies between the modules. So coupling occurs when there are interdependencies between the one module and another, which is the number of interfaces that we have. The number of, in fact, the picture here tells 1,000 words. So this is really bad, and this is really good. Because one module works with this module, this module works with this module, this module works with this one, and the relationships are fairly clear. When we start doing this, it's bad. It's actually bad programming practice too. Even in the, this would be like using functions correctly. This would be like having multiple functions that do the same thing, that don't have self-identifiable, and both concepts actually work together. When you have a low level of cohesion, you have a high level of coupling. Because the scanner module is working with the printer, the print module is working with the print function, it's working with the scan function, it's working with the input function, it's working with the printer, it's working with all of these other things that, you know, it's confusing as to what it's supposed to be working with. And then you pull it out, and it's not easily replaced. So where interdependencies exist, changes in one place will require changes somewhere else. So when you pull this module out, or you change the implementation, the fewer number of interfaces it has, the easier it is to change and modify. And the newer module doesn't have to be, you know, doesn't have to do everything. It only needs to do what it's supposed to be doing. So the network of interdependencies makes it hard to see at a glance how the components work together. So when you have one leading to one, sometimes, you know, this one has two. So this guy here uses two different modules as well. So, but this, you know, you don't want 3, 4, 5, 6 of them. You know? So it's basically, there's no set number of connections as a guideline. There's no set number. It depends on the size, quality, characteristics of your program. But theoretically, you want to reduce the number. So you have very low coupling going on. You also want to use layers in your design. And you've got that already because you've got the architectural design, hopefully. And here's some examples of some layering. And here's the typical layers in an application program. We have the user interface. We have the application logic, or the application. And we have the database access, and the operating system access, and the network access. And it's fairly clear, actually. And it's layered in terms of the abstraction. Here's typical layers of the operating system, typical layers of a communication system, and we can take each one of these little boxes here and break them out into other sublayers. When we see the layers, we're seeing the level of detail. So when we do layering, and let's say in our program, we have the user interface, and we have the accounts payable, the accounts receivable, the reporting, and then the reporting's got, you know, system reports, tax reports, customer reports, invoices, you know, all different types of reports and stuff, and that can be broken out into other layers. That works with this, and kind of looks like module decomposition. Kind of looks like the architectural design. It is. It's just another way of presenting it in terms of the abstraction. Keep the level of abstraction as high as possible. That's another good design goal, which is why you start out with an architectural design. Because the interesting thing is, like, you know, you're building this device, and you've got all these specs for it, and the programmer's been working on it for 6 months, and he comes up to you and says, you know, I don't understand this interface. And you say, well, this interface is this way because that's what the cell phone needs. in order for the user to talk into the receiver. And then the guy comes back and says, "This is a cell phone?" Doesn't even know he's making a component that works on a cell phone. Because then, that's why you needed it this way. So, I mean, the lower level details of implementing a hardware component or a software driver or something can be understood from the lower level implementation just fine. But sometimes decisions have to be made that affect the appliance that's running in. How much heat is this throwing off? How much heat should it throw off? Are you going to burn? The receiver's coming up to the user's head. Is it going to burn the user if it's too hot? Do we need a fan in there? Or, we don't have fans in cell phones. We never have those issues. But we use components that avoid that problem. But anyway, long story short, the example kind of leading into, without seeing the big picture, without seeing the high level of abstraction, it's really hard to see the context for what you're building these components for. Ensuring that the design allows you to hide or defer considerations of detail, thus reducing the complexity also. So you can take it from a couple of different angles. In order to understand the little pieces, you got to understand the big picture. And understand the big picture, you got to hide the little details sometimes so you can see the big picture. This is a computer. Some of these devices nowadays, are kind of easy, but who in the world knew about, actually a lot of people don't know about these things. They're called hotspots. They look like little USB keys. You plug them into your phone. It makes your phone into a hotspot. A lot of people don't even know the concept of the device. We all know what computers are. We know what tablets are these days. We know what cell phones are. But we got a bunch of new devices coming out that work with these things, that create new concepts. So it's nice for the consumer, but it's also nice for the developer to know what it is they're building in terms of the interface. Of course, everybody knew what a microwave was, hopefully. Modern day stuff. But yeah, no, actually it's really cool. It's like a little thing. It works with a USB cable, like you plug it into your computer. You plug this thing into your phone, and it gives your internet access at your house. It's a hotspot, essentially. It creates a hotspot for you. Verizon's selling them now. And they are having unlimited data on them, but the unlimited's going away. So we'll see what happens with that product. So a good abstraction is said to provide information hiding, and abstractions allow you to understand the essence of the subsystem without actually having to know the necessary details of the implementation. We also want to increase reusability where possible. And this is what they throw down constantly in an object-oriented design arena. They say reusability, increase reusability. It's been a long time. It's been around a long time before object orientation. So design the various different aspects of the system so that it can be reused. So you can gain it. Can be used again and again in different contexts and different systems. And if you're a software development house and you're making networking applications, I would definitely use reusability in terms of a design concept. Why reinvent the wheel every time you got to do a connection? Just use the same protocols, use the same stuff over and again. Once you learn how to do it, you've perfected it, hopefully. And now you're good at it. And there's less bug, error checking, and stuff like that in the future as well. So generalize your design as much as possible, following the procedures of the 3 design principles: cohesion, coupling, stuff like that. Design your system to contain hooks, so you can easily hook a new component in. Simplify your design as much as possible. Keep it short and simple, as I say. Reuse existing designs in code where possible. So you're a software development company and you don't want to go into business for the first time all over again every time you have a new project. Hopefully you've got a good format for your requirements doc, and you have a good format for your design doc, and you've perfected the change control process, which we're going to be talking about soon, and you've got all your standards down and your practices down. Well, reuse them. Create a practices manual for the new people who come in to learn how the old people have been doing stuff, so you can train. So design with reusability and complementary to design for reusability. So designing and reuse is complementary for design and reusability. So actively reusing design codes allows you to take advantage of the investment that others have made in terms of reusable components. And this doesn't mean selling the same program to the customer, to 10 different customers and calling it the same. That's not the same. That's plagiarism. that's copyright infringement. What I'm talking about is perfecting practices and reusing the same practices, perfecting design code, the way you're designing the code and using that over again. And certain things aren't proprietary, such as generally accepted protocols. accesses, the database designs and things. That stuff is not exclusive to one particular application. But no, you don't want to build one application and sell it as a different application to 10 different people, although that does happen. Design for flexibility. Because requirements change, the world changes before the project is actually done. People ask for new stuff all the time. Actively anticipate changes if possible that the design may have to undergo in the future. You're building an application that works with wireless 802.11g. Let's say you're back in the B days, and G comes around, or H comes around, or I comes around. Well, make it so it's flexible. You can actually easily, customer just upgrades through the internet with a new driver or something. Or what about it just not even be hard set? There's a text file or something, and they just change a setting. Oh, all of a sudden we're compatible. So, reduce coupling and cohesion. Actually, who did this recently? I was really impressed. Not going back to Verizon, but they have 4G compatible devices. Well, they don't have 4G out yet, but you can buy 4G compatible devices. So you can just upgrade your service, so you don't have to buy a new phone or a new tablet or something. So that's actually designing for flexibility, actually. Yeah, but the problem with that, though, is how do you know that the implementation of the hardware is going to be 100% compatible until you actually have the service available? If you think of it, they haven't tested it yet. So I guarantee you there's going to be a recall on half of those products that are 4G compatible. Replacements, firmware updates, because there's going to be issues with it. Reducing coupling, increasing cohesion, creating abstractions, not hard coding anything, leaving all the options open, creating parameters, not restricting the options of people who have to modify the system later, and use reusable code and make code reusable. Here's a good one you're all going to like, anticipating obsolescence. It's going to be obsolete. Well, actually, this is what Verizon's doing with that upgrade. 3G is going to be obsolete soon. Actually, your iPhones are going to be obsolete soon. You guys hear there's a new iPhone on the market or in development, probably out in September. So, you know what? I can guess you right now it's probably going to be thinner. And let me guess, 4G compatible? 5G compatible? I don't know. So, 3G is not enough anymore. So it'll just be like the iPad, a little thinner, a little faster. Thinner, faster, thinner. Pretty soon it'll be a piece of paper. So. Alright, but that's anticipating obsolescence. So, actually that's what people used to do with cars. They used to sell their car every year because there was something brand new out that's better. So, well, or actually, people nowadays have the exact opposite thinking because cars are so expensive. Keep it, buy it, keep it forever, even though gas prices have gone up. That's why they got those old clunkers. Turn in your clunker, get a new car, hybrid or something. So. Avoid using early releases of technology because they're not proven yet. And avoid using software libraries that are specific to particular environments, only works on Windows. And what if Windows XP didn't go away, but what if it did go away completely? All those XP programs would be obsolete. So. And avoid using undocumented features of little used features of software libraries. This happens all the time. Somebody in the tech support made a fix, or somebody, some back-end programmer made a fix to the driver so it works, but you upgraded your operating system. Now it doesn't work. Something happened. Or it's not supposed to be used for this, but it works. How long is it going to work for? You don't want to base your entire application on it. Avoid using software or specific hardware from companies that are less likely to provide long-term support. Don't buy a Daewoo. They're not in business anymore. Of course, they made some good TVs for a while. They made cars, TVs, microwave ovens. They made everything. They branched out all over the place, and then they went bankrupt. Actually, you can't get your Daewoo car serviced anymore. In fact, most of them are garbaged, totaled. Use standard languages and technologies that are supported by multiple vendors. Actually, use Java. Yes. Java will give you portability, but it will also give you reliability. Turn in obsolescence. So you can always upgrade your JVM for the program to work. So, design for portability, having the software run on as many platforms as possible. and avoid the use of faculties or specifically one particular environment. It only works on Windows, which is kind of interesting. .NET only works on Windows. So that's, I don't know, from a portability or an obsolescence kind of thing. And you know how many versions of .NET they've got out already? Well, I think we're on like number 3 or 4 by now. It's like, I don't know. A library only available in Microsoft Windows would be a good example. For portability. Does Windows work on a tablet? No. Does it work on Android? No. Would a Java app work? Yeah. So, I don't know. Now, I'm not totally anti-Windows, but they're not very cross-platform compatible. They're often to be obsolete. Depends on the version of Windows you're working with. Here's an interesting one. Design defensively. You know, so I always use the joke where I once rented a car in New York, and you get out of the parking. You know, when you're driving out of the rental car place and you see the signs, you know, freeway this way, buckle up. The sign said drive defensively. Over here in California, it says drive safely. In New York, it says drive defensively. Because you gotta watch out for the people on the road. They're all crazy. Defensively. So, same thing applies to software. Design defensively. People are going to break into your software, steal it, reuse it, hack into it. So never trust how others will try to use the component you are designing. Even your own software team will try to try to do something that's unethical, or might also try to do something that you didn't think was appropriate in terms of handling a particular component that you created. Handle all cases where other code might attempt to use your code inappropriately. Check that all of the inputs and the components are valid, preconditions. Unfortunately, overzealous defensive design can result in unnecessary repetitive checkings. Yeah, like 12 password checks to get into the main menu or something, or excessively slow running system because it's checking everything. Highly defensive. So, techniques for making a good design decision: using priorities and objectives to decide among the alternatives. That's actually the biggest technique. But here's some steps. You want to list out and describe the alternatives for the design decision. If you're trying to, come out at this point, maybe you've already decided on which design you're going to go with for your design document, because that makes you decide. After you've done all your analysis, you got to pick an approach at one point. So you can kind of list out everything and then pick, or list out the advantages and the disadvantages of each one of the design decisions with respect to the objectives and priorities that you have set in mind. Which is, if you're working with a Microsoft environment, you might actually say that you have to do a .NET application. And this is not going to work. This is only focused towards Microsoft users. It doesn't work, unless you're in that environment. Then that might make your decision right there. Determine whether any of the alternatives prevent you from meeting any one of the objectives in the requirements document. And choose the alternative that helps you best meet your objectives. And then adjust the priorities for subsequent decision making. So you're in tune, so you don't make a decision in the future that counteracts a previous decision that you've made. So, these are antiquated, and some of these might make you laugh, actually. This is a very old examples. Example priorities and objectives. In terms of security encryption, must not be breakable within 100 hours of computing. Yeah, on a 400 megahertz Intel processor? Wow, no, that would be outdated, actually, in terms of today. So it's CPU efficiency. Network bandwidth, 8 kilobits. Ooh. Memory, must not consume over 20 megabytes of RAM. That's like, what? Maybe 2 gigs of RAM these days. Portability, must be able to run on Windows 98, NT4, Windows ME, as well as Linux. Wow. I keep this slide in because it's like a blast from the past, and how computing has changed over the years. Okay, we're slowly getting to the end of this. Software architecture. Actually, let me take a look here. Importance of good design, a good design document. You know what? We're coming up on our time. Do we want more? Do we want to? Because I could split this out. I think I normally split this out, and I stop at this point, actually, in terms of software architecture. Let's do it. Let's split it out. Someone remind me, next week we are starting on slide number 26, and we're going to, because this goes into a little bit more details in terms of the layout and it's better if you have a fresh perspective when you start listening, because it's going to go into actual writing this particular document to give you the end features of the design document. And I'm going to go over the design document yet one more time, so for those people who missed it last week. So, okay, so we're done for today. So have a good one. And for whoever wrote it down, it's slide number 26 of lecture 13. Lecture 13.